Hi everyone, this video is for lecture 3, Managing Quality, topic 2, Product Design. So in the previous topic, we reviewed normal distribution and the standard normal distribution. So using standard normal distribution and normal distribution, we can apply this knowledge in this area called product design. So let's start with the definition of design specification. So in a company, when you produce a product, how can you decide whether this product is defective or not? There must be a standard, right? So this standard is used to compare, and the products or services are designed based on this quantitative specifications or standard, and it is called the design specification. So the format of design specification looks like this. So there is one target value. So in the best case, so the target value. However, the machine and the labor you are using is not perfect. So you have to allow some tolerance. So upper tolerance, and here lower tolerance as well. So tolerance. So based on this tolerance, so target value plus tolerance is called the upper specification limit. So here, upper specification limit, and I'm using abbreviation USL. And the target value minus tolerance is called the lower specification limit or LSL. So when you produce a product, let's measure some output. And this measurement is inside this range. So for example, here, or even the perfect target value, we say that those products are not defective because it's still inside this design specification limits. However, when you produce a product and the measurement of this product is outside this limit, like outside upper specification limit, or even outside the lower specification limit, those products are called defective product. Okay, so using example, you may better understand the concept of design specification. So here, the design specification of the depth of a desk is given as 2.15 centimeters plus minus 0.09 centimeters. So from here, what we can find, this format is design specification, then target value must be 2.15 centimeters. And what is the tolerance? Tolerance is given as an error that is allowed, so 0.09 centimeters. Then, what is the upper specification and the lower specification? That is the question. So actually the answer is given, but how to get this answer? Upper specification limit is USL equals to target value plus tolerance. Therefore, it is 2.15 plus 0.09, and this will give you the answer 2.24. Lower specification is similarly target value minus tolerance. Therefore, in this case, 2.15 target value minus tolerance 0.09. So the answer is 2.06. So now you understand the meaning of upper specification limit and the lower specification limits. Okay, so given this design specification, now let's talk about yield rate. So what's the yield rate? Yield rate, by definition, is the percentage of non-defective products when the process output follows a normal distributions. So this means, let's say when you produce a product and when you measure a output, whether it's depth or width or whatever, let's say that is X. So X may have many different values because X follows a normal distribution with average mu and standard deviation sigma, and then graphically we can describe this x output of the product using a normal distribution curve like this. Then the center value is mu and the standard deviation is sigma. Then when you use design specification as a standard, how can you decide whether product is defective or not? You may find the upper specification and the lower specification. Again, here, when you use design specification, lower specification limit means target value minus tolerance. Upper specification limit means target value plus tolerance. So when a designer set these limits, the target value in general that may be matched with the average of actual outputs. It's not always true, but if production environment is normal, majority of products may get this target value as an output dimension. So therefore, if it's normal process, many times the average of your output may be matched with the target value. Okay, then how can we describe this LSN USL? Let me use a different color. So suppose this average value is about target value. Then with given tolerance, here on the right side you may have, if it's a tolerance, upper specification limit. And on the left side, with the same tolerance, you may have a lower specification limit. Then you still remember the meaning of normal distribution curve. So the area under this normal distribution curve means what? If there is a value x1 and x2, we know that this area is a probability when x is between this x1 and the x2, right? Given this, if you look at our current curve here, what this area means? This is actually means that's percentage of non-defective products. Or this area is called what? Yield rate. So in summary, the yield rate is the probability when product is not defective. That means when product output is between this lower specification limit and the upper specification limit. So the probability when X is between LSN and USL is this red area. So that is yield rate. And note that the area on the tail side here on the right and on the left here, this is what probability when you find the products are defective. Example 2, if the design specifications for a certain dimension of a part are 2.15 centimeters plus minus 0.09 centimeter, if the process output for this dimension is normally distributed with process mean, so mu, and process standard deviation, sigma, then what is the yield rate? So again, design specification, who set up this design specification? Designer. So a designer decided that his product's target value equals to 2.15, and the tolerance in this format you can find it's 0.09. So that's design specification. In this case, process mean is indeed matched with this target value. But as I mentioned before, it's not always the case. What this means is target value, it's a kind of designer's subjective decision. But this process mean means after you run this process to produce many products, the data you get from this production is used to calculate this process mean. So therefore, actual process mean could be different designer's target value. But if designer set up the target value well or wisely, I don't know. But anyway, in that case, the target value can be matched with this process mean, right? So in this special case, we can draw a distribution like this. So that is actual distribution. So when we use a process, what does it say? The mean value is 2.15. And what is the standard deviation? 0.03. That's from the process. And then we want to compare this actual output with the designer's specification. And the designer says, here is the center line, and that's matched with the designer's target value. That's good sign. And the designer allow tolerance, and the tolerance is given as 0.09. So this line is 2.15 plus 0.09, and this is another tolerance. 0.09 is given, so 2.15 minus 0.09. So what's the yield rate? Yield rate is the area under here between lower specification limit and the upper specification limit. So now what we can do, there are many ways you can get the probability. You may want to convert this into standard normal distribution like we have done. But in this case, it's a little bit easier because if you look at these two values, it is kind of special case. So 2.15 plus 0.09, what this part means. So this is relevant to sigma. So 0.03 is a sigma. Then how many sigmas is matched with 0.09? Actually 3 sigma, right? So this is actually mu plus 3 sigma line. And the other side, this is similarly, we can say it's mu minus 3 sigma line. So when it is mu plus 3 sigma and mu minus 3 sigma, it is a kind of special case, right? In that special case, we know this area. Even you don't need to convert it into standard normal distribution. If you want, you can do it. But in this case, we already know the area is 99.7%. Okay, so we can get this yield rate by converting normal distribution to standard normal distribution as well. So by definition, yield rate is probability when X is between lower specification and the upper specification. So we know these boundary values. So what we need to do here, we have X distribution, and the X's to boundary is 2.24 and 2.06. But we do not have any distribution table for X, but we have to convert it into Z, right? So here, if it's Z, the center line will be matched with 0. And we have to know this Z1 value and this Z2 value. Okay, so how to get the Z1 value? Z1 value is, this is X value, so X 2.24 minus what is the average 2.15 and over what is the standard deviation 0.03. So therefore you will get 3 for this value, Z value, and actually that's matched with mu plus 3 sigma and this number, 3 times of sigma. And the Z2, similarly, you can find 206 minus 2.15 over 0.03, and you will get minus 3. So therefore, we easily figure out yield rate is when probability, not X, but now it's Z, the value is between minus 3 and 3. Okay, so using standard normal distribution table, we can get this yield rate. So I will not show you all the details, but when you use your standard normal distribution table, what you can do here, minus 3 and the 3, and if this is the area that we are looking for, actually we can think about 2 times of this yellow area, right? So how to get this yellow area? This yellow area equals to, if you know this standard normal distribution table when z equals 3, this area minus 0.5, then you will get this half area. And then if you have this, so the first one you will get from the table, and if you subtract it, and if you multiply this by 2, so the answer would be 99.7% if you got the correct answer. Please check it by yourself.